Hi everyone, today we are diving into image analytics using R and we will go step by step from loading the image, training the model, and finally analyzing the result. Now let's get started. Before we do any deep learning, we have to set up our environment. I have prepared a setup guide for you for both Mac user and for Windows users. Because I am on my Mac right now, so my illustration mostly use the setup guide for Mac. All right, so let's do it. So you can download the setup guide using the link in the video descriptions. And I also show the description on the screen right now, just for your preference. And let's do it now on the terminal. All right, just a note that you might want to consider to install the Python version 3.11 that will work stably with all the packages required for our analysis today. So just in case, if you look at the screen right now, because I already installed the Python, so I don't need to reinstall that. Just in case if you didn't install any Python before, so just go ahead and install the software. Next, I will create a virtual environment. And then I will activate that virtual environment. So the virtual environment here named R TensorFloat. And now it's time for me to install the TensorFloat. Okay, why we need to do this? Deep learning in R relies on a package called Keras, but it actually uses Python and TensorFlow to do the heavy lifting. So we need to make sure R can talk to Python and use the TensorFlow library. All right, now we are ready to tell R to use a specific Python environment where the TensorFlow is installed. All right. Okay, so first we need to use the package reticulate. And you can install the package and just run it once because I already installed, so I don't need to reinstall the package. I just call the package. Now I will tell R to use the virtual environment where the TensorFlow is installed. Now I will check which Python version and the libraries that our R is using. Excellent. So you see the Python version 3.11 was installed and the TensorFlow package was also successfully installed. Now we can call the library TensorFlow. Good. And now we will test if the TensorFlow is installed correctly and can access our central processing unit or not by running this code. Excellent. If you see a notification like this one, it means that you already installed TensorFlow successfully into the virtual environment, and this library can access our central processing unit. Now our environment is ready. So let's install and load the R packages that we use throughout our analysis today. So packages in R, like the language modular, like you need to plug in the tools that you need for the job. In particular, we have several important packages like Keras, like EB image. Okay, so you can run everything in this step at once because the way it is written to avoid reinstall the existing package and you only install the missing package. So it's safe to run all the codes here at once. Great. Now let's move on to the second step. We load our image metadata. Before we start working with the actual image, we need to load a file that contains metadata for each image. In particular, in this case, we need an Excel file that include all the useful information like whether the image has a human in it or not, whether it shows a logo clearly or whether it's colorful, and so on. This data will help us later on when we try to understand what makes an image popular. Now, let's open the file. Okay, so let's just have a quick look at the file we just uploaded. So you have the first column, you have the image ID. The second column, you have the classification, whether the image is popular or not. The next column, whether the image is colorful or not. The next column, whether we have a human in the image or not, whether the logo is shown clearly or not, and whether the product itself is shown clearly in the image or not. Great. All right, so now we can look at a couple of images from our dataset. One popular image and another one is an unpopular image. This will help us understand what the model will be seeing. All right. Of course, we will use a lot of more image later on, but it's good to inspect a few first. All right. So if you look at this image, it's quite clearly the logo is shown in the image, right? And this is classified as popular. Now, if you look at this image, it's a little bit busy, so a lot of things there. And this image is classified as unpopular. And again, the deep learning model can look at thousands of images at the same time, but our human brain can learn a lot just by looking at one like we just did. Now let's move to step number 4. We need to load all the images that we have. In particular, here in this case, we have 20 images, 10 popular and 10 unpopular. And we need to split them into the training and test sets. Okay, before we moving on, I need to explain to you a little bit regarding the data division into training set and test set. What are they? All right, if you look at the image shown on the screen right now, so you will see the data is divided into different parts, right? When training a model, we don't just use all of our data at once. Instead, we divide it into 3 key parts: training, validation, and test sets. So what is the training? Training data is the largest part. This is what the model actually learns from to understand the patterns in our data, right? Next to the training, we have validation set. This is a smaller portion of the training set used during the training to fine-tune the model hyperparameters, like the learning rate, like number of layers, like the prop out rate. And it helps us decide when to stop training and avoid the overfitting. Good. Once the model is fully trained and tuned, we use the test data. This is a completely untouched dataset to evaluate how well the model performs on new unseen observations. And this gives us a realistic idea of how it would behave in the real world. In short, training data teach the model, validation data tunes the model, and testing data evaluate the model. All right, so right now we need to load all the image that we have. Basically, we will create a vector that store the name of the image file that we have in our folder. So in the first 10 are the 10 popular image, and another 10 are unpopular image. That's it. And the vector will look something like this one, like 1, 2, 3, 10. And the first 10 here are the popular image, and starting from 11th, 12, and so on until 20. So the second half will be unpopular image. That's it. Great. So we have the vector. Now we just load all the image that we have into that list. Good. Now it's time for us to divide the data into training and test sets. So in the training set, we will keep a popular image and a unpopular image. And in the test set, we will keep 2 popular image and 2 unpopular image. Let's run the code. All right, and we also need to resize all the image to 400 by 400 pixels because deep learning models need image to be the same size. Okay, this idea is very simple. Imagine trying to train a model where some images are very huge and others are tiny. It wouldn't work well, right? So let's do it. Now let's have a look at how training set look like. Great. And here is how the test sets looks like. Excellent. In step 5, we need to create the label for classifications. Popular image will get a label of 1 and unpopular image will get a label of 0. And these are we call binary classification labels. All right. So right here we create the label for the training set. Right here we create the label for the test set. And because the deep learning model in R relies on the Keras package, so it is important we need to install the Keras package to the virtual environment we created in the beginning. So you need to run this step. So in this case, because I already installed Keras, so right here it responds that Keras is available and ready to use. But for your case, you might see the Keras package is being installed, right? And after we have the label for popular image and unpopular ones, we need to convert those labels into a format that our deep learning model can work with, what we call categorical labels. All right, so let's build our model. We are using a type of neural network called a convolutional neural network, or CNN for short. And CNN models are really good at analyzing the image. They work by scanning the small part of the image at a time, kind of like how your eyes scan a photo. All right, so let's start to explain the idea of CNN a little bit. If you look at the architecture diagram of CNN on the screen right now, you will see first we have the input layer. Basically, input layers are all the images entering the network as a matrix of B-cell values. And after that, we have a convolution layer. So multiple filters slide or scan over the image and will detect the patterns like edge, textures, and shapes. This is where the model begins to learn the visual features. And after the convolution layer, we have the pooling layer. This layer reduces the size of the feature maps while keeping the most important information. It's helped to make the model learning faster and more efficient. After pooling layer, we have fully connected layer. This layer will flatten all the pool features and connect all of them together. This layer acts like a traditional neural network. And last but not least, we have the output layer. And this layer will produce the final classification result. And in this case, it might be predicting whether an image is popular or unpopular. All right. So I already prepared the note for every single live code. So please take some time to read as you need. And right here, we only need to run the model itself. Okay, step 7 is quite interesting. This step like putting all the photos into a neat, organized album before showing them to a teacher, right? So before we train the model, we need to reshape the image data again into the format that the CNN model expects. So basically, CNN model expects all the image in a 4D array, including width, height, color channels, and the number of image. And we do this using the apron function. So let's do it. All right, here we are. Now step 8, training the model. So in this model, we run 30 rounds of learning from the training data. And we also use the validation split. So we can monitor how well the model is learning and if it's starting to overfit. So let's train the model. Okay, it might take a while and then we can analyze the result. All right, so based on this result, what do we see? So the top of the plot, it shows the training loss and the validation loss. Okay, so the training loss is in blue color. It decreased consistently and stabilized around 0.5, which is typically a good sign. And then the validation loss in green. It behaved differently. It stayed relatively high and increased over time and spiking after around the 10th round, right? And the other bottom of the plot, it shows the accuracy of the training set and the validation set. The training accuracy improved rapidly and reached nearly 100% around 10 rounds of training. It shows the model is memorizing training the data. Why? For the validation accuracy remains stuck around 0.25% throughout the entire training process, which is very low. And this confirms the model is not generalizing at all. It is overfitting significantly. So of course, in reality, it's quite common. And you need to do something else. For instance, simplify the model, reduce the layers, like adding the new data. Remember, the data set for this case is only 20 images. It's quite little. And of course, right here, I show you another way to plot the result of the model. Okay, and the interpretation is still the same. All right, step 9, evaluate the model on the training set. It means that we test the model on the same data it trained on. So we will check its predictions, calculate accuracy, and rare confusion metric to see how often it got things right or wrong. Okay, so before we move on, let me explain a little bit on confusion metric. All right, as you can see on the screen right now, that is what we call confusion metric. It is a powerful way to evaluate how well your classification model is doing, especially for binary classification problems, like predicting whether an image is popular or not. So you see the rows represent the predicted classes, what the model thinks, and the column represent for the actual, the true classes. Therefore, possible outcome, TP, true positive. The model predicted positive and it was actually positive. For example, it predicted the image is popular and the image is really is. FP, false positive. The model predicted positive, but it was actually negative. It thought the image were popular, but the image wasn't. And then we have FN, false negative. It means the model predicted negative, but it was actually positive. So basically the algorithm missed a popular image. And we have TN, true negative. The model predicted negative, and it was really negative. It correctly identified a popular image. So this metrics give a deeper look than the accuracy index alone. It's help you understand how the model is right or wrong. Okay, so right here, I will compute the accuracy on the training set. So you see the accuracy is 81%. So high training accuracy is great, but we also need to check the test accuracy to see if the model really performed well on the future observations or not. Okay, and this lab code help you to predict the class probability. Basically, we are computing the probability for class popular and class unpopular, right? And if the probability is larger than 0.5, the label will be 1, and vice versa. All right, and right here, we will show what confusion metric we have. Okay, so again, here is what we just computed, the probability for each image. And here is the predicted class, what the model think. And here's the actual class, what is the true class of each image, right? So the simple confusion matrix will look like this one. You need to analyze what 5 means, what 8 means. But I will show you another advanced technique how to illustrate the confusion matrix by using ggplot, right? Okay, if you look at this confusion matrix, it means that the model have 8 times correctly identify popular image as popular, and the model have 5 times correctly identify unpopular image as unpopular. And right here, I will show you how to compute the accuracy more manually. So basically, we take all the time the model correctly identify the image divided by the sample size of the training set. So we have 13 divided by 16, which is 81.25%. Right. All right. Now, the real test. Let's see how well the model performs on the new image it has never seen. We need to calculate the test accuracy, look at predictions, and build another confusion matrix. All right, so let's do it. Everything's the same. Basically, we just rerun the analysis on the test set. All right, so what do we have here? So basically, looking at this confusion metric, the model only have 2 times correctly popular image as popular. All right, and the accuracy is 50%. All right. So again, the test accuracy tells us whether the model is learning the real patterns or just memorizing the training image. And of course, when you practice with deep learning or image analytics, you will know we have many ways to improve this kinds of test accuracy. All right, so far we know the future image will be popular and unpopular if we use the training model. But we also want to know whether these popular image have certain features in common, whether unpopular image have certain features in common, and that is what we are going to do in step 11. First, we need to select the image predicted to be popular based on the test set analysis result, right? Remember in the metadata, we have the last 4 columns are the metadata for each image. We need to extract those informations. And last but not least, let's use the simple plotting functions to tell a story. All right. So again, this step will help us to interpret what the model may have learned about popularity or unpopularity. Reporting the accuracy is good, but it's not enough. We need to use deep learning to tell a story, to inform a managerial decision for the company. That is even more important. How you run the algorithm. So if you look at this result, what is your story? How will you help your company? based on image analytics, using image analytics. All right. So right here, based on this result, if you are the marketing specialist, what will you inform the decision for your future marketing campaigns? So in the test set right here, the model likely never see the grayscale image. It only see the colorful image, which means the colorful image might be good for your future campaigns or promotion campaigns. Interestingly, all images are not human-centric will be identified as popular, including a human subject in your shooting campaigns may not be that useful as you thought. And right here, on the image, have a logo exposure. So if logo present is a key factor, the model will predict the future image as popular. Right here, if you have some variation for product exposure. And again, I just use tiny data set to illustrate how to do image analytics. The model might be overfitting because it doesn't have enough data to generalize for the future data. So if you start your image analytics project, it might be brilliant to collect more data as you could. Right, and that's it. We just built and evaluated our first image classification model using deep learning in art. And feel free to post, rewatch the video, and try the analysis with your own dataset. Good luck.